Because I feel like I could use at least 2 weeks off before I.
Yeah, you should take a break before
I just
you
want to be
start.
able to unwind, maybe actually fully clean my apartment. I've been cleaning it, but like not nearly as much as it needs to be. My roommate doesn't do it anyway. But he pays all my rent, so I'm not exactly gonna pull her at it.
Yeah, he's like speed reader.
So I am with his class.
Yeah.
Like, he tries to people finish grading, and I literally finished it an hour afterwards.
Oh my gosh. You're just getting hundreds away.
For documents, so nice. It's like over the breaks. Break these like late ones, and he lets me turn in grades.
Luckily, I think I get to talk about FEA for stuff. So I'm glad that I took that class.
Nice, that's good.
I was like, oh, Dr. Tran got me a job.
I didn't get your job. You got yourself a
Yeah,
job.
yeah.
Was that Steven?
Yep. He just left.
Really want to joke with him about how I was telling you about the downfall thing I watched. And I was like, I would never work with Troy, but I'm afraid he's gonna get really defensive. So I'm just gonna stick to making fun of you.
Wow. Me, the one with the moral, with the high moral job.
Yes. But you can take it, so it's fine.
Yeah.
And I think that, I don't think I don't talk to you, but I thought it was hilarious that your girlfriend was like totally playing along with being her
Oh,
fake
yeah.
girlfriend.
I told her everything about it, and she's like, "That's funny."
Weren't you here? Logan?
Okay.
Oh my gosh. That's awareness. In your surroundings.
Not a date.
When you said, did you go to office?
Yeah.
It's like then the tax comes from behind, he's like, it's so attacked from behind. He's like, yeah, I slapped him. That's you right now.
Yep. Gonna be working on MATLAB today?
I'll be demonstrating a MATLAB code, although it's just a follow along type of thing. So
Any plans for the weekend?
we have like a welcome day on Saturday. So for like the incoming freshmen, we're welcoming them and letting them know how great our department is.
Yeah.
So I'll be here at 8:30 in the morning on Saturday.
Oh, you have to come to that too?
Well,
Yeah.
it's a long story, but I need to work harder, and so that's why that's why I'm there.
Were you voluntold?
Well, I was guilt tripped into.
That's annoying.
Wisconsin.
It's too late at this point.
Yeah.
How about you guys?
I think I'm gonna be going to Palm Springs tomorrow evening. I'll be there over the weekend.
Oh, nice, nice. Before?
Just gonna be with the girlfriend and her family.
Oh, nice.
Yeah.
I have to come to the Be a Titan thing too.
Oh,
And
okay.
a table for 2 tables.
Oh, okay.
Yeah.
So I'll see you there maybe.
Yep. We can try to blend in with the students table with us.
Yeah, maybe. We'll see. Sorry, just noticed the chat. No, I need to be there. Am I able to bring +1s? Yeah, I could. But I don't think my wife wants to wake up that early on a Saturday.
They initially made it voluntary for clubs, and then they all of a sudden made it mandatory.
Yeah, there's a lot of that. There's a lot of that going on this year.
Yeah, I think it's because they were scared that no other club would want to do it on Saturday.
Yeah. There's been a lot of changes at the administrative side of the university this year. That's been they've been a little bit tougher on everyone. So I think that's probably why as well. All right, it's 5:30, so let's go ahead and get started. All right, good evening, everyone. How's everyone doing today?
Good.
Hanging in there? Good, good. All right, so we're gonna be just chugging right along today. And so last time we left off, we started out with 2D problems with finite volumes, and so we're gonna be continuing on with that. And so today we're gonna talk about how to do boundary conditions in these types of situations, and then we're gonna look at a code. Okay. And then after that, if we have time, then we'll start the next set of lecture notes, which is on convection with finite volumes. Okay. All right, and so I think that's it. Not too many announcements today. And so you guys know that there's a homework due next Wednesday, and so make sure you guys are working on that. And if you have any questions on that, as always, you can just let me know. All right, so there are any questions I can answer before we get started? Okay, all right, so let's go ahead and continue. And so let me scroll up a little bit, just because I think it's kind of a nice place to leave off. And so last time we were working on the 2D diffusion equation. So let me go and scroll. We're working on this one right here, right? And so here is our 2D diffusion equation. And so we have a minus k multiplied by the divergence of the gradient of phi, okay, which is equal to our source term, q of xy. And so of course, since we're doing the finite volume method, we place our governing equations here in vector form. Okay? Then we went through the usual process. We integrated these equations, and then we used our integration rules to eventually obtain our algebraic equation. Okay. We did quite a lot of steps last time, but I want to kind of focus on this step right here. Okay. So remember, when we took our double derivative of our diffusion term, we use the divergence theorem to break it up into 4 integrals, right? And so what we have here is basically our 4 integrals. We have our integral on the east edge, the integral on the north edge, the integral on the west edge, and the south edge, right? So this is kind of the hallmark of how to apply finite volumes in 2D. And so, whenever you apply finite volumes to a governing equation, you always end up with multiple integrals. And each of those multiple integrals represent the flux of some kind across those different edges, okay? I know I kind of wrote it in kind of a weird spot here, among the other notes, but we'll be talking about this quite a bit, throughout throughout today, throughout next week when we talk about convection, right? And so it's this idea that when you apply finite volumes and you basically perform a control volume analysis on your individual cell, then what you're going to obtain is basically these flux terms which describe how your quantity of interest is being transported across that edge, right? And so let's think of I think the simplest example here, where phi represents, say, like a temperature. So we're looking at a heat transfer situation. Okay. What each of these integrals represent is it represents how much heat is passing through each side or each edge of our cell. Okay. And so I want you to kind of keep that interpretation in mind as we go along, because eventually in the end, if you kind of remember where we ended up, we end up with an algebraic expression here that looks basically the same as our finite difference, right? And so it kind of seems like, we did all this math here, all this integration stuff, and we end up in the exact same place as before, right? But the interpretation is the key, and the interpretation is kind of what really sets the finite difference and the finite volumes apart. For these kind of, we consider them kind of more simplified problems, which is just straight up diffusion, straight up convection. The two look very similar. Finite volumes, finite difference look very similar. But when you apply the same methodology, the same kind of mindset to a more complicated equation like Navier-Stokes, that's where you start to see a lot of the big differences between finite difference and finite volumes. Okay. But that interpretation of you apply finite volumes to an equation, and you get each of these different flux integrals, that's going to be key to us moving forward. Okay? And so with that in mind, let's take our equation now and let's talk about how to apply boundary conditions. Okay. Okay. So let's do Dirichlet first. So let me go ahead and draw you an image here. Okay. And so let's say that we're considering the following cell. And so we have this cell here, right? So we call this phi sub c because that's the center cell that we're looking at. Okay. Then, of course, we have its north neighbor, we have its south neighbor, and here we have its east neighbor as well. Okay. But on the left side, instead of, or say on the west side, instead of having a west neighbor there, what we can say is that this cell borders a Dirichlet boundary. Okay. Right. And so this side of the cell right here This is a Dirichlet boundary condition. Okay. It's a Dirichlet boundary condition with value of phi none. Okay. And so remember what Dirichlet boundary conditions mean. And so when we have a Dirichlet boundary condition, that means our solution value or our the value that we solve for, it must be phi 0 on that edge. Okay. And so when we had this situation in finite differences, it wasn't that difficult to account for, right? Because in finite differences, remember we were working on the nodes of the system. We're looking at the vertices, right? And because of the way our meshes are structured, right, we had vertices or we had nodes that sat right on that boundary, right? And so when we went to go apply the boundary conditions, all we had to do was to say that for each of these nodes that sat on the boundary, then their solution value has to equal phi none, which is the specified value, right? That's all we had to do. With finite volumes, our task is a little bit more difficult here because we're not solving for the vertex values. What we're solving for instead are the self-centered values. Okay. And so since the self-centered values don't sit directly on the boundary, we can't simply just say that phi c is equal to phi none, right? Because that wouldn't be correct because phi sub c doesn't sit on that boundary. And so because it's offset just a little bit, and it might be just a very little bit, we can't exactly say that, okay? But what we can say is that if we look at phi sub c here, right? And let me draw a green box around it just to kind of make it a bit more clear, right? Right. This is the cell that we're concerned with right now, okay? And so for that particular cell, we can see that its west edge or the west side of that cell, that's what's sitting on phi none, right? And so how this is going to affect our solution is that the only integral, remember we have 4 integrals, right? So we have a north integral, a west integral, south and east integrals, okay? Right, so the fact that the Dirichlet boundary condition sits only on the west side, that means that the only part of our equation that's going to be modified is that west integral, okay? All the other integrals are going to be unchanged. Okay? And so the way that we're going to treat these boundary conditions is that we're going to write out our 4 integrals again, or at least, we're going to get them to the point where, that we have to start plugging in. And then from there, we can take the west one and then replace it with an expression that has this Dirichlet boundary condition. Okay. All right. Any questions on this? Okay, so let's take a look and see what that looks like mathematically. Okay. And so if we start from a point from our diffusion integral, okay, and so this is taken from a part. I'm not exactly sure where we got to this point, but this is after we applied the trapezoidal rule. And so we're starting from this point right here. Okay, and so we've basically taken each edge integral and then converted it using the trapezoidal rule. Okay, so this is after trap rule. Okay, and so we ended up with the following expression. And so we had partial phi, partial x, evaluated on the east edge, multiplied by delta y, plus partial phi, partial y, evaluated on the north edge, delta x, minus partial phi, partial x, evaluated on the west edge, delta y, minus partial phi, partial y, evaluated on the south edge, delta x. And so you can see here we have 4 separate terms that come from the four edge integrals. Okay. So normally what we would do at this point is that we would take these derivatives here, right? So no matter what these represent are the solution derivatives at that particular edge. Okay. Remember, the way that we plugged in for these is we assumed that the solution varied linearly between the two self-centers. Okay. Okay. And so if we assume a linear variation, then the slope of that line would be phi sub e minus phi sub c, all divided by delta x, right? And that was kind of one of the last things that we did in order to obtain our algebraic equation. Okay. And so we can do that for most of these terms here. And so because we have an east neighbor, right? We have a north neighbor and a south neighbor. That means all of these ones right here are good because we have neighbors on those sides. Okay. The only one that is not good is the west one, right? Because we don't have a west neighbor. And so we're going to have to modify this expression right here to account for the Dirichlet boundary condition. Okay. And so we're going to do basically the same thing that we did in the 1D case. And so if you remember from the 1D case, what we did was we took our we took a difference like before, okay? Right. And so here we take a difference between the self-centered value phi sub c and the Dirichlet value phi sub naught. And then we're going to divide it by the distance in between them, right? And the distance in between the self-centered value and the Dirichlet boundary is delta x divided by 2, right? So remember, delta x is the length of a full edge length here, okay? I don't know why my iPad's been cursed this week, okay? And so if delta x is the length of a full side, then to travel from the self-center to the boundary is only delta x divided by 2, okay? And so that's why I substitute that with delta x divided by 2. Okay. Okay. All right. And so from here on out, we've basically made the substitution, and we just got to simplify at this point in order to get our algebraic equation for that one. Okay. All right. Any questions on this? Okay. All right, so let's go ahead and let's go ahead and continue on. And so just to make our lives a bit simpler, let's go ahead and assume. Let's assume that we have even grid spacing in both directions. Okay, so that means delta x is going to be equal to delta y. It's equal to delta. Okay, and so that's going to cancel out a lot of the delta terms here. Okay. All right, so let me go ahead and write out what we obtained from that. And so we have a minus k, this multiplied by phi sub e minus phi sub c. Okay, so this is the contribution from the east edge integral plus phi sub n minus phi sub c. Okay, this is the contribution from the north side. Then we have the contribution from the Dirichlet edge, which is the west side, right? So this can be 2 phi sub c minus 2 phi sub naught. Okay. And then finally, we have the contribution from the south edge. That's phi sub c minus phi sub s. All right, so let's go ahead and simplify this a bit more. And so we have a minus k multiplied by phi sub e plus phi sub n plus phi sub s minus, let's count the number of phi sub c's that we see. And so we have a minus 1, minus 1, minus 2, minus 1. Okay. And so that in total is going to be minus 5 phi sub c. Okay. And then on the outside here, we have a 2k phi naught. Okay. All right. So the reason I put the 2k phi naught on the outside of the parentheses here is because this is a known quantity, right? We already know what phi naught is because that's the boundary condition, right? And so what we can do is we can take this term right here and move it to the other side of the equation. Okay. So this is a known quantity, so we can go ahead and move it over. Okay. And so putting this together, and so putting this together with our source term, okay, when we put this together with their source term, we get our algebraic equation for a Dirichlet boundary. And so we have a minus k phi sub e plus phi sub n plus phi sub s minus 5 phi sub c. Okay. This is equal to q at xc yc delta squared. Okay. That's our source term. And so we went over that kind of at the very end of lecture on Monday. And then we're going to add 2k phi naught. So that's the algebraic equation that we're going to obtain for this for that cell that borders that Dirichlet boundary. Okay. All right. Any questions on how we obtain this? Okay. All right. So you can see that this process that we went through is pretty pretty lengthy, right? And so I want to kind of take a step back and let's talk about some of the trends that you can see, because when you're applying these kind of in real time, it helps to kind of know what these trends are, just so it kind of speeds up your work. Okay. So this is I'll call these observations. Number one. And so, let's look at this equation right here, and let's compare this to our interior node equation. Or excuse me, interior cell. Okay. Okay. And so we scroll back up here, we look at the interior cell equation. You can see our interior cell is phi sub E, phi sub N, phi sub S, phi sub W, minus 4 phi sub C, okay? Right, and so we compare that to this one, you can see the biggest difference you see is that phi sub W is absent, okay? Right, and so we don't have a contribution from the neighbor that borders that boundary, right? And so in this case, the Dirichlet boundary condition was on the west edge of our cell. And so of course, we're not going to have a phi sub W because we don't have a neighbor over there, because it's just the boundary there. Okay. All right. And so, when you're forming these boundary condition equations, kind of the easiest way that I think to do it is to take the interior cell equation, which is the most general one, and then make modifications to that equation depending on if you're on a boundary. Okay. And so the first modification you have to make is that, if you have the neighbor or the edge of that cell borders that boundary, then you take off that corresponding neighboring value. Okay. All right, so that's the first change that we have compared to the interior value. Okay. The other change that we see is in the coefficient for phi sub C. Okay. In our interior cell equation, we had a -4, right? We had a -4 phi sub C. This one, we have a -5 phi sub C. Okay? And so for every Dirichlet, basically for every Dirichlet boundary that you have on the cell, you're going to decrease the phi sub C coefficient by 1. Okay. Number 2. The other observation that we make is that, the Dirichlet boundary condition, that one that has to show up in the equation in some way, that one's moved to the other side of the equation. First of all, with a positive sign. Okay. It's moved to the other side of the equation with the positive sign, but you also have to multiply it by 2k. Okay. And one more observation, which doesn't have to do directly with this Dirichlet boundary condition, but it's kind of a general observation in general. Okay. And so unlike finite differences, right? So remember when we did finite differences and we were at the boundary, the boundary condition became the equation, right? And so in other words, we basically replaced our algebraic equation with the boundary condition, okay? In finite volumes, we take a very different approach. And so instead of replacing an equation, what we have instead is that our boundary conditions are going to modify our usual finite volume equation, okay? Okay. And that's a really important distinction. And so basically what you're going to get with finite volumes is that you're going to get basically almost the same algebraic equation for every single cell in your mesh. The only thing is that it's going to be modified compared to the usual one. Okay. Right. And so even though this cell here borders the boundary, we didn't come up with a brand new equation for it just for the boundary condition, right? We took our existing equation, which had our 4 face integrals, and then we modified it to account for the boundary condition, okay? That's gonna be really important because, next we're gonna go over Neumann boundary conditions and we'll see how that's modified. But we're also gonna have cells that border more than one boundary, okay? And so for our cases, the only time you'll see that is when the cell is existing in the corner, right? And so in the corner, it borders two boundary conditions. Okay. And so for these cells that border more than one BC, before in finite differences, we kind of just ignored them. But now we can actually do something with them because instead of replacing an entire equation, all we have to do now is just apply this modification more than once. Okay. Okay. And we'll do an example of that. Later. All right. Any questions on any of this? Okay. All right. So that's Dirichlet boundary conditions, and that's actually the more difficult one. And so now let's do Neumann boundary conditions. Okay. And just like the Dirichlet boundary condition, I think this is usually best explained with an example. Okay. And so let's say that we have a cell here that borders a Neumann boundary on its south side. Okay. So we're going to have something that looks like this. So this here will be phi sub c. This phi sub east, the east neighbor, phi sub west, and phi sub north. Okay. And on the bottom here, we have a Neumann boundary condition where the flux or the derivative of the solution there is going to be gamma, which is going to be our specified Neumann condition. Okay. All right. Okay. And so you can see here we have neighbors on the west side, the east side, and the north side. And the only place we don't have neighbors is on the south. Okay. And so we're going to start in the same place as we did before. And so we're going to start with our diffusion integral. Okay. And again, we start at the point which is after the trapezoidal rule. And so we have minus k, partial phi, partial x on the east face, delta y, plus partial phi, partial y on the north face, delta x, minus partial phi, partial x on the west face, delta y, minus partial phi, partial y on the south face, delta x. All right. And so just like we did before, we're gonna make the normal substitutions here when we can. And so for this case, since we have a west, east, and north neighbor, all of these we can make the normal substitutions. Okay. Okay, and so since we have neighbors on those sides, we can make the substitutions there as normal. Okay, so nothing too bad there. Okay. For the south integral, of course, here we're going to make a substitution involving the boundary condition. Okay, and again, for the Neumann condition, it's really easy because because we have the derivative here that's already kind of baked into the equation. All we have to do is just replace this. Which is the exact quantity that we have. And so we have partial phi, partial, well, it's partial n here, but it's partial y because n is in the y direction. We just have to replace this with gamma. Okay, and so let's do the same thing as before. And so let's assume a even grid spacing. Once we do that, we have a minus k, then we have phi e minus phi sub c, okay, plus phi n minus phi sub c, okay, minus phi sub c minus phi sub w, okay. Then we have minus gamma delta x. All right. And so let's simplify this. And so we simplify, we have a minus k, phi sub e plus phi sub n plus phi sub w minus 3 phi sub c. Okay. We only have 3 here because we completely replaced the west side integral. Okay. Okay. And then on the outside here, we have a k gamma delta x positive. Okay. Because we have the positive, we have the negative from the minus k and the negative in front of the gamma to cancel out. And so we end up with positive. Okay. And so just like before, we're going to move this to the other side because it's a known quantity. And so if we do that, we end up with the following equation. Okay. So we have minus k phi sub e plus phi sub w plus phi sub n minus 3 phi sub c, okay, is equal to q at xc yc delta squared minus k delta gamma. Okay. So there's our equation for a Neumann boundary condition. Okay. All right. So let's look at some trends just to make things easier for us when we apply this in an example. Okay. Of course, the first thing that you notice is that phi sub s is missing. Okay. Again, that's because we don't have a neighbor on that south side, and so we can't that can't appear in this equation. Okay. If we look at the coefficient for phi sub c, you can see it's +1 from what it was before, because before we had a -4, now we have a -3, so we just added 1 to that coefficient. Okay. Right, so next thing you notice is the Neumann condition appears on the right-hand side. Okay, and at first you see, and first you see here it's with a negative sign. Right? Of course, we're multiplying by k and delta as well. Right? But you have to be careful here with the sign, and so here we have a minus sign. But this only occurs when the Neumann condition is on the south or the west edge. Okay. If the Neumann condition was on the north or the east edges, then it's going to appear on the right-hand side with a positive sign. And so we can use these observations to kind of, give us a little bit of a shortcut when we're working these through by hand. All right, any questions on this before we do an example? Okay, so let's go ahead and do an example and see how all of this works out. Oops, let me switch back to black. Okay, and so let's consider the following domain. Okay, so we have our square domain, right? On the bottom here, let's say we have a Dirichlet boundary conditions. We have phi is equal to 25. And right here, we have a Dirichlet boundary condition, phi is equal to 50. On the right-hand side of here, we have a 0 Neumann boundary condition. So the flux is going to be 0 on that side. And on the top here, we have another Neumann condition, but it's going to be equal to 10. Okay. And the equation that we want to solve is this one here. Right. So I think we've solved this equation, a couple of times already. And so just now we're going to do it with finite volumes. All right, and so let's do this on a grid where we have 16 cells. And so the way we're going to break this up is we're going to do it's like that. Okay, and this will be cell number 1, cell number 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right. And so, before, I have this solved in code too, but before we jump into the code, I want to, do a couple of these cells by hand, just so that you can kind of get practice applying the applying the equations that we've done up here. Okay. All right, and so before we start that, let me go ahead and write out the problem parameters. And so based on this equation right here, right, you can see here that the coefficient out here is 1, okay? And so you have to be a little bit careful here because the sign kind of tricks people up a little bit, okay? Because normally, because the way that our equation is written out right here, we have a minus k out in front, right? And so in order to get a positive 1 in front of this parentheses, that means our k here has to be equal to minus 1, okay? And then our source function is going to be whatever's on the right-hand side, which is 3xy. All right, any questions on the setup for this this example here? Okay. All right, so let's start with the interior cell. That's always the easiest to start with, okay? Remember, with finite volumes, we work really hard to get this interior cell equation, and that kind of forms a template for everything, okay? Okay, and so for the interior cells, we have minus k multiplied by phi sub n plus phi sub e plus phi sub s plus phi sub w minus 4 phi sub c. It's equal to q of xc yc delta squared. Okay. And so if we have an interior cell that has neighbors on all 4 directions, then we can just go ahead and apply this directly to that cell. Okay. And so let's search up an interior cell. We have 4 here. And so let me do cell number 6. Okay. It's the first interior cell there. Okay. Cell number 6 here fits the criteria for an interior cell because we have a neighbor on all 4 directions. Okay. And so if we apply that and we apply k is equal to minus 1, we get the north neighbor. So the north neighbor for 6 is 10. Okay, so this is going to be phi 10 plus the east neighbor. The east neighbor is 7 plus the south neighbor, which is 2 plus the west neighbor, which is 5. Then we have minus 4 times phi sub c, so this is minus 4 phi 6. Okay. And then next, what we have is the source term. Okay. We can assume that the grid here is going. This problem I have 1.5, and so what we have here is 1.5 in each direction. Okay. And so when we apply this here, then we have 3xc yc. Okay. You would normally compute the coordinates for that cell, but I'm a little bit lazy right now. Okay. And we multiply that by delta squared. Okay. Delta being the grid spacing in each direction. All right, so that's an example of applying our interior equation to an interior cell. And so, it's just kind of straight up just how we normally do. Okay. All right, any questions on this? Okay. All right, so next let's do an example with a Dirichlet boundary condition. And so let's do cell number 3. Okay. And so for cell 3, we have a Dirichlet boundary condition on the south edge. All right, so remember the way that we modify this is that we take out the south neighbor, and so we don't have any contribution from that. And then we decrease the coefficient for phi sub c by 1. Okay, so we're gonna have a minus 5 instead of a minus 4. And then the Dirichlet boundary condition is going to appear on the other side. Okay. And so if we do that, First, we have contributions from all the neighbors. And so we have phi sub 7 plus phi sub 2 plus phi sub 4. Okay. So those are all the neighboring cells to cell number 3 here. Then we're going to have a minus 5 phi sub 3. Okay. Then we have a 3xc built squared, where again you would need to know the coordinates for cell number 3, which is going to be different than cell number 6. Okay. And then to that, we're going to add with a positive sign 2 times k times the Dirichlet value. Okay. Where k here has a value of -1. Okay. And for the south, for the south boundary here, phi naught is going to be equal to 25. Okay. And so to get this equation, remember, I just started with our usual interior equation. I made the modifications that have to do with the Dirichlet boundary condition. And then I just kind of reported it as it is. Okay. So that's the,
Quick question.
yeah.
So it still be minus for the 2K,
It would be, yes. And so for the Dirichlet boundary condition, you're always going to end up with the positive sign over there. It's the Neumann boundary condition that you have to worry about the sign. Yeah. That's because for the Dirichlet boundary condition, because we kind of replace this this guy with another kind of finite difference, basically, then the sign of this and the sign of this kind of cancel each other out. And so you always end up kind of with the positive sign over there. Yeah. Mm-hmm. Okay. So that's cell 3. So that's a Dirichlet boundary. Now let's do an example with the Neumann boundary. We could do one on the east, but that's kind of boring because it's 0. So let's do cell 15 here. Okay. All right, so for cell 15, we're going to start out with the left-hand side. And so first we have all the contributions from the neighbors. And so the neighboring cells for cell 15 are 14, 16, and 11. Okay, so we have phi 14 plus phi 16 plus phi 11. Then we have the contributions from phi sub c. But since we have a Neumann condition, we're going to change this to 3. Okay, and so we're going to add 1 compared to the interior cells. Right, and then on the right-hand side, we have 3xc, okay. And then on the other side here, we're going to have our contribution from the the contribution from the Neumann boundary condition. But this, remember, this one, the Neumann boundary condition is on the north side, right? And so on the right, it's going to appear with a positive sign. Okay? And so we have a positive. We have a positive k times delta times gamma. Okay, okay, so remember, positive sign. Positive sign here. I don't know why that line keeps appearing. It's a positive sign because the Neumann boundary condition appears on the north side. Okay. Right. And of course, k here is -1, and gamma here is a 10. Okay. Any questions on how we obtained that? Okay. All right, so I want to do one more example before we jump into the code, and I want to show you a corner cell. Okay, because a corner cell is unique because it borders more than one. It borders more than one boundary. Okay, so let's do cell. We have 4 options here. Let's do cell number 1. Okay. All right. So cell number 1 here borders two. It borders 2 Dirichlet boundaries. Okay, so it borders a Dirichlet boundary on the south, and it borders one on the west. Okay. Okay. And so we're going to apply the same technique that we did to modify for Dirichlet boundary conditions, except we're going to do it twice. Okay. All right. So first we have to include the contributions from the neighbors. And so the only neighboring cells for cell 1 are going to be cell 2, which is its east neighbor, and cell 5, which is its north neighbor. Okay. Then we have the coefficient in front of phi sub 1. Okay. So remember, for each Dirichlet boundary condition that you're going to subtract 1 from this term. Okay. And so if we start at -4 and we subtract 1, we get -5. We subtract 1 more time, and we get with the -6. Okay. Okay. Then we have the source term, which is 3xy, and we multiply by delta squared. Okay. And then we have contributions from the 2 Dirichlet boundary conditions. And so we have a 2 times k times we'll go the south one first. Okay. And so the Dirichlet boundary condition on the south side is 25. Okay. Then we have to add the contribution from the west Dirichlet boundary condition, which is 50. Okay. And so you make 2 additions to the right-hand side. Right, so corner cells are not that difficult to do. You just have to apply the rules twice. Okay. All right, and so you can repeat this process. And so if you look through the notes, I've written out the equations for all 16 of the cells. But of course, here we're not going to do that because it takes a bit too much time. Okay. All right, any questions on this before we jump into the code? Okay. All right, so let's go ahead and jump into the code. All right, so I posted this code onto Canvas for you. Okay. And so if you go to week 11 of our course website, you can see here I have a 2D diffusion FVM code. Okay. So the code is completely done, and so you don't have to modify anything. It's just kind of there for your reference. Okay. Okay. And so we're going to go through this code here and kind of walk you through the logic, because the logic for this code is actually a bit different than what we've seen before, and it has to do with the fact that we're evaluating each integral kind of separately on the domain. Okay? And that's generally how these finite volume codes are written. So it's written in a way that you evaluate each integral, each edge integral, all 4 of them. You do them individually based on that. All right, so first we have the top section here. So the top section is all more or less the same. And so here we define the length of the domain. We have the number of cells in each direction. And so I guess I have 100 here. And so we have 100 by 100. And so that's fine. Okay. Then we have the total number of cells. We have the grid spacing. We have the left-hand side matrix, right-hand side vector, and our k value. So usual stuff here. Okay, so then we go to section 2. And section 2 is when we go to populate the left-hand side matrix and right-hand side vector. And so, this is going to be a bit different, based on our, based on what we've done. Okay. All right, so first you can see here we have a nested for loop, and so we have a loop over I and a loop over j. Okay, so this is standard stuff, and so we still have to loop over all the cells, and so that's kind of normal as usual. Okay. Next, we compute the ID numbers, right? And so, we use the same kind of node numbering scheme, or excuse me, cell numbering scheme as we did in finite differences. Okay? So even though we're labeling cells now and not nodes, we can use the same numbering scheme. And so we kind of label horizontally first, and then we kind of stack on top of that. Okay, so here we get to the biggest differences. And so, I want to spend a bit of time kind of explaining the logic behind these if statements here. Okay. Okay, and so what I've done here, and so let me actually add another note because it's not really clear here. What I'm doing in this if statement is I'm evaluating the east and west integrals together. Okay. Okay. All right, and so what you can see here is that I'm checking to see if we're on, if our west edges are on a boundary, our east edge is on a boundary, okay? And if so, I'm going to be making a modification to the code, okay? And if not, then I'm going to, just kind of do the normal thing, okay? So I think the best way to look at this is to start from the bottom, because this else statement here, this is the case when both neighbors are present, okay? And so in other words, we are an interior cell, okay? Right. And so let's start with the else statement first, because that's the easiest one to look at, and then we're going to go look at the boundary cases, okay? And so when we have an east and west neighbor, right, the thing that we're going to add is we're going to add a minus k to the west slot, right? Right. And so this represents the coefficient in front of phi sub w. Okay. It's minus k here because remember we have a minus k out in front of the equation. Okay, so I basically just took that minus k and multiplied it through. Okay, so we have a coefficient of minus k in front of phi sub w, and then here we have a coefficient. This is the coefficient in front of phi sub e. Okay, which is also a minus k if we're an interior cell. Okay. Okay. And then the coefficient in front of phi sub e, or phi sub c, excuse me, right? And so if we have neighbors on the left and right, you can see here that I've added a positive 2k. Okay, so you're probably like, wait a minute, if we're an interior cell, this should be a 4k, right? Because that's what it means to be an interior cell. For this if statement, we're only covering the two left and right, so the west and east one. Okay, and so if you sum up the contributions from just those two, then those two integrals only contribute just a total of 2k to phi sub c. Okay, the other 2k, if we're in a totally interior cell, will come down here. Okay, so this other if statement down here, this is the contributions from the north and south. Okay. And so that's where the other 2k comes from. So that's why here I only have a positive 2k. Okay. And so once again, if we're at an interior cell, we have to add the contribution to the west neighbor. We have to add the contribution to the east neighbor. And so that's what these two lines of code do. Okay. And remember, the contribution that you add is a minus k. And then you also have to add the contribution to phi sub c, which in this case is 2k. Okay. And of course, the other thing that you notice here is that I'm using my update notation. And so when we're adding coefficients here, we don't want to overwrite what's there before. And so we say that the new value of this slot is equal to what was there before, right? Plus a new value. Okay. This is especially important here because we're going to be kind of visiting the same locations, more than once. And so it's important that we don't override, what was there before. Okay, so that's kind of the logic behind the interior cell. And so the only time that we execute this is that if we're not on a west boundary and we're not on an east boundary. Okay, so does that kind of make sense to everyone why we use this logic here for the interior cell?
Explain over time for the 2K.
The 2k here.
Yeah.
Yeah. So we have a 2k because normally, if we're at a completely interior cell, we have neighbors on all four sides, we'd have a positive 4K, right? But here we're only evaluating the east and west integrals together. In total, you're gonna evaluate eventually all four integrals, right? North, south, east, and west. But the north and south contributions are going to come a little bit later in the code down here. And so because we're only doing just the two on the east and the west, then those only contribute 2K to the phi sub c.
Oh, I see. So you split it up from the top portion is the X direction and the bottom is the Y.
Exactly. Yeah. Yeah. Mhm. Okay. Okay. So that's the interior cell. So now let's go over the logic for the boundary conditions. Okay. And here's where our rules are going to come into hand. Okay. So first thing we're going to check is we're going to check and see if we're bordering a west boundary. And so we're going to check. And so you can see the if statement here is if I is equal to 1. Okay. And so if I is equal to 1, that means we're on the very left side of our domain. Okay. And so in this case, we're bordering the west boundary condition. And if you go back to the figure in the notes for what this problem looks like, that means we have a Dirichlet boundary condition for this problem. Okay. I emphasize for this problem because I think the homework problem that I gave you is different. Okay. And so for a Dirichlet boundary condition, let's go ahead and apply our rules. Okay. And so if we're on a Dirichlet boundary condition, first of all, you can see that we have no A my ID, West ID, right? We don't have that here because we don't have a west neighbor, right? Because we're on the west boundary. Okay? And so we don't have that. And so we only have contributions to my ID, which is phi sub c, and then my ID, east ID, which is phi sub e. Okay. Okay, so let's look at my ID first. And so you can see here that we add a contribution of plus 3K. Okay. And so this is to represent the fact that when we have a Dirichlet boundary condition, we subtract 1K, or we just subtract 1 from the Dirichlet condition. Okay. We subtract 1 from the phi sub c, but then we multiply by minus k out in front, and so that's why it becomes a positive 3. Okay. And then on the east side, this doesn't change, and so this is kind of the same as the interior boundary, the interior condition, because we have an east neighbor, and so our east condition is not going to change in this case. Okay. Okay. And then if you look at the right-hand side, then we have to add a term to account for the right-hand side. So we can see we have a 2, we add a 2 plus a k multiplied by 50 here being the Dirichlet boundary condition on this problem. Okay. And so this is the contribution to the right-hand side that comes from the Dirichlet boundary condition. Okay. Okay. But the key here is, instead of adding a plus 2, which we did for the interior cell, we had a plus 3 instead because it's a Dirichlet boundary condition. Okay. All right. Any questions on that? Okay. All right. So next we have the Neumann boundary condition, and we're going to apply the rules for the Neumann boundary condition. Okay. And so for the Neumann boundary condition, this is when we're on the east side, right? If you look back on the problem figure, we have a Neumann boundary condition of 0 on the east side of the domain. Okay. And so in that particular case, then we add instead of adding a plus 2 to phi sub c, we only add a plus 1k. Okay. Next, we have the contribution to the west neighbor. And so since the west neighbor is unchanged here, then we have just a simple minus k. And then on the right-hand side, we're going to add the contribution from the Neumann boundary condition, which is a k times 0. And this 0 here being gamma. Okay. And then we're going to multiply by dy because that's the formula for the Neumann boundary condition. Okay. Okay. And so it looks, this does look a bit intimidating. I know it's quite a bit different from what we've experienced. But kind of work through the logic here. And I think probably the best way to work through it is to start from the bottom. Start from the bottom where you have both a neighbor on the east and the west, and then kind of use that and as a reference for how to get these coefficients for if we're on the west side, which is the Dirichlet boundary condition, or if we're on the east side, which is the Neumann boundary condition. Okay, any questions on this? Okay. All right, so that's the logic for the east and west, or the x direction integrals. So now let's look at the y direction integrals. But this is going to be kind of more or less the same. Okay. The only difference here is that instead of east and west ID, now we're going to be working with north and south IDs. Okay. So once again, let's work from the bottom and kind of let's start from the bottom and work our way up. And so if we look at the else statement here, and so if that basically means that we're not on the west side of the domain, we're not on the right side of the domain. And so that means, or excuse me, not on the north side of the domain or the south side. And so that means we have neighbors on the north and south edges. Okay. And so in this case, we do our normal thing. And so we add a 2k to phi sub c. Okay. We add a minus k to phi sub s. And we add a minus k to phi sub n. Okay. Right, so same logic is up there. And the boundary condition logic is the same here as well. And so if j is equal to 1, that means we're on the south boundary. Okay. And on the south boundary, we have a Dirichlet boundary condition. And so because it's Dirichlet, we add a plus 3k instead of a plus 2k. Okay. And then for the north neighbor, that becomes just a minus k. And then on the right-hand side, we add a 2k times 25. And 25, that's because 25 here is the Dirichlet boundary condition for that edge. Okay. And then similarly for the north boundaries. For the north boundary, we have a Neumann boundary condition. And so we add just a single plus 1k on phi sub c. And then we have a minus k on phi sub s. And then we add the contribution from the Neumann boundary condition, which is a plus here because it is a Neumann condition on the north side. Okay. Okay. And so I think that's probably the most complicated part of this code right here is to kind of logic out what these two if statements are doing. But remember, focus for the finite volumes, you really need to kind of think of these from the integrals point of view. And so you should think of it as, how do I evaluate my east integral, my west integral, my north integral, and my south one? And then how do I put that in the code here in order to kind of represent that? Okay. Any questions on this? Okay. All right, and so the last part here is that we have to account for the forcing function. And so the forcing function is 3 times x times y. Okay. And so in order to do that, we have to get the x position of this particular cell. Okay. And so we can see here that I'm computing the coordinates of the cell centers. And so the way that we do that, remember the cell centers are not the same locations of the nodes. And so you need to offset the x and y by a half grid spacing. Okay. Okay, so this is like an offset for the fact that our cell centers are in the middles of the cell, not on the edges. Okay. And so the emphasis here is that we're not looking at the coordinates for the cell for the cell nodes. We're looking for them at the cell centers. And so that's why I have this 0.5 times dx, and then we add the usual I minus 1 times dx. And same thing for y. Okay. And then once we have that, then we just look at the right-hand side of the equation and we add the forcing function. Okay. And then we multiply it by delta squared. So that's the dx and dy right there. Okay. Okay. And so all that is good. And so let's go ahead and run this code. So the rest of it is fine. And so the only thing I added here was just some timing and the usual plotting stuff. Okay, so let's go ahead and run the code. And I think I've downloaded this code more than once this week, and so it's angry with me. So let me go ahead and rename this. Okay. You can't have spaces in your MATLAB code names. Okay, so this took about 4.5 seconds to run. And here is the plot. Okay. So it looks very nice because I ran it with the 100 by 100 grid. And so it's a pretty fine grid. Okay. And so if you compare these results, and so this problem here, I gave it to you on purpose because we ran this exact problem when we went over 2D diffusion and finite differences. Okay. what you should see is that, even though, we're computing the values here at the cell centers and not at the nodes, your result should look the same because it's the exact same problem. It's just that the way that we approach it is different. Okay. And if you compare the way that your code looks here compared to the way your code looks over there, right, with finite differences, obviously this looks really different, right? And so, I think this is kind of a nice thing because, it kind of shows you that even though you're using different methods, right, one's finite difference, one's finite volume, you're going to get the same solution in the end because they're both methods for solving the same kind of problem. If you held them up kind of right next to each other, they're not going to be exactly the same because they're different methods, but overall, they give you solutions that look very, very similar to each other. All right, any final questions on this? Okay, all right, and so that's it for 2D finite volumes. And so when we come back on Monday, we'll start talking about how to do convection with finite volumes as well. Okay, but you should be fully equipped now to do the homework. So I believe the homework is just based on diffusion with finite volumes. So you should be able to do everything there, and the homework is due next Wednesday. Okay, so thank you everyone for tuning in today. Hope you guys enjoy the rest of your day, rest of your weekend, and I'll see you guys on Monday. Thanks, you too, Eddie.
Can I ask you a question for you? In your notes, you said when you're like looking at the contributions, I guess, or observations for the Neumann.
Yep.
You wrote that phi c coefficient is +1.
Yeah.
Like how? Because like when you're looking at the equation that you wrote for phi c, it's -3.
Yeah.
So like how?
It's +1 relative to the interior. No, so the interior equation had a -4 phi sub c,
Oh, I see.
and for the Neumann you add kind of +1 to
Got
that
it.
minus.
Okay.
Yeah, I do it like that because you're going to come, and so if you look at that example, so I think I have the equation written out for the top right cell. I think it's cell 16.
Mhm.
So that one borders 2 Neumann boundary conditions, and so instead of -4, the coefficient for that will be -2 because you add -4 +1 for the two Neumann boundary conditions.
Okay. I see.
So it stays at -6, or
It's -6 if we have 2 Dirichlet boundary conditions.
Yeah.
But if you have 2 Neumann boundary conditions, it becomes -2.
okay. So for the okay. So then for like the cell at 1, how did that go by again? Because I know that is it like -5, and you're adding a +1 because of the extra Dirichlet? That's what.
Yeah. So cell 1 there, it's at a corner, right? And so it has two boundary edges. And so it has a Dirichlet boundary condition here, Dirichlet boundary condition here. And so we start with -4, and then say for this Dirichlet boundary condition, we do a -1.
Right.
And so instead of -4 becomes -5.
Mhm.
And we do another -1 because the bottom is also a Dirichlet. So we have -5 -1,
Okay.
which is -6. Yeah.
Cool. Thank you.
Yep, no problem. Any final questions from Zoom before I close it up? Okay, all right. I'll see you guys next week.